All right. So 5(1) is all about inverse functions. An inverse function can be done a lot of different ways. We're going to do it with ordered pairs, equations, graphs, all kinds of different ways of looking at inverses. I'll give you the actual definition of an inverse, but then we'll talk about really what we're doing and what's happening. So the definition of an inverse is to interchange the first and second coordinate of each ordered pair. So what I will typically say is we're just going to switch x and y. It's kind of a quick and easy way to say it. The reason I don't necessarily state it like that is because your variables may not always be x and y. But typically x and y is what we think of when we think of an ordered pair. So if we think of an ordered pair as x, y, we're just going to interchange or switch the x and the y around, and they're going to trade places. Okay? And then what we're going to do today is we're going to do a little bit of graphing and that kind of thing when we do that. When it's defined by an equation, bless you. We're going to switch the variables of the equation. I'm going to give you some examples here of writing an inverse. First one I'm going to give you an example of is doing an ordered pair, and then we'll do an equation just to kind of show you that, I mean, basically it's the same thing. And then eventually we'll work into what does a graph look like, and then talking about some of the things that it might mean. Okay, so let's say that I gave you h. And we're going to write it as a function or in a set of ordered pairs. And so I'm going to say negative 8, 5, 4, negative 2, negative 7, 1. And then I'm just going to kind of throw this one in there just to show you that it doesn't really matter if it's decimals, fractions, negatives, positives. That is the set for h. It's just bunch of random ordered pairs, basically. And if I ask you to find the inverse of h, we're essentially just going to switch the order pairs around. So negative 8, 5 becomes 5, negative 8. 4, negative 2 becomes negative 2, 4. 1, negative 7, and 6.2, 3.8. And these are just brackets showing that we're putting it in a set. Same number of ordered pairs, right? We have 4 ordered pairs, and we're just flipping all of those ordered pairs around. Pretty straightforward on how to rewrite and put it as an inverse. Now, one of the things that we're going to talk about a little bit today is the original a function? How would we determine if this here is a function? Yeah, none of the x values are the same. All the x values are different, so that means this would be a function, okay? And that's what we're going to be talking about today is functions. So the same thing here, right? If I wanted to determine if the inverse is a function, once again, I look at the x values of the inverse. All of the x values are different. So both of these are functions. because x does not repeat for either. So if it ever asks you if the original and the inverse are functions, that's all we really have to look at. If we're looking at ordered pairs, that's pretty easy to determine. In a little bit, we're going to look at graphs. How do we determine off of a graph if we don't have like a list of ordered pairs like we have here? But if we have a list of ordered pairs, that's pretty easy to know. Okay. If I give you an equation, y equals x squared minus 5x. And I ask you to write the inverse of this. What we talked about just a few minutes ago was all we have to do, x becomes y becomes x. So we're just going to interchange the two variables that we have. So when I rewrite this equation, that's all we got to do. That is my inverse equation. Eventually, we're going to talk about if this is actually a function or not. Okay? And for this one right here, I'm not going to worry about that because there are going to be times where we just say what's the inverse and we don't determine if it's a function or not. But we will do that a little bit today, and I'll show you how to do that if we have an equation like we have here. Okay. So that is the inverse of an equation, inverse of some ordered pairs, a couple of different ways that we can determine inverse of something. Say, my daughter had that one time, and it was not a fun weekend when she had it. So have a fun weekend, Maddie. Graph a function and its inverse on the same graph, okay, just to kind of see what's going to happen here. So I'm going to give you kind of a basic function here. Y equals x squared plus 1. Okay, just a quadratic equation, something we're pretty familiar with, right? And we can obviously put this into our calculator, but we're not going to necessarily be able to do that with the inverse. So I'm going to show you a really quick and easy way to do this. So what I would do for this is when I graph the original here, I would come up with some ordered pairs. And you can come up with those ordered pairs off of your calculator if you want to, okay? Ordered pairs aren't going to be real hard to generate here. I'm going to plug in 0, I'm going to plug in 2, and I'm going to plug in -2. Just going to pick, I'm going to pick a positive, a negative, and 0. And you can plug in whatever numbers you want, but those are the numbers I'm going to choose. So it's just kind of random, right? But just 3 numbers to choose. And the reason I'm choosing a positive and a negative, I'll show you why here in a second. But I'm going to start with 0. 0 squared is 0. 0 plus 1 is 1. When I plug in 2, 2 squared is 4. 4 plus 1 would be 5. When I plug in -2, -2 squared would be 4. 4 plus 1 would be 5. So those two end up being the same y value. We already know what the graph should look like because we've talked about quadratics a lot. We know it should make a parabola. And you could get all that information from your calculator. I don't have a problem with that one bit. But then when I ask you to graph the inverse of this function, this is where coming up with some ordered pairs is really kind of helpful because I can't put this into my calculator, right? I can't take this equation and type it in my calculator. I'd have to solve for y and solve for y, and that one would be really difficult to do because of the squared in the equation. And so the reason I generate some ordered pairs is because now when I graph this, we know that when we do the inverse, we're just going to switch the x and y around. So this is going to become 5, 2, 1, 0, and 5, negative 2. So I take the three ordered pairs that I just came up with, I flip all three of them around, and now I'm going to graph this. So there would be the inverse graph. Hey, couple of things here. Whenever we do an inverse, this will be helpful to know, I think, just because whenever we do an inverse, this equation right here is my reflection line. Okay, that kind of goes back to geometry, I know. We're taking a graph and we're reflecting it over a line, and we did a little bit of we're doing that right now in geometry, to be honest with you, and where we're taking a graph and reflecting it over. This y equals x line is my reflection line whenever I do an inverse. And the reason why is because this line right here, my ordered pairs would be 1, 1, 2, 2, 3, 3, 4, 4. All the y's and x's are the same. So when I switch x and y, then it just takes the graph and flips it over that line. X becomes y becomes x. And so now it's been flipped over that line. So if you ever want to know, does my graph look correct or not, you can always draw this y equals x line from the bottom left to the top right, and it should look, this should reflect over to get right on top of this. Okay? And that's just kind of a visual more than anything to kind of see what should my graph look like and be able to determine if it looks correct. Okay? Now, a couple of things I also want to talk about while we got this graph up here. Is this a function? How do we know if a graph is a function? What did we do earlier in the year? Line test, right? We're going to take a vertical line and we're going to run it across here and we're going to determine if it's a function. Well, it is because it only touches one point at any given time. Is the inverse a function? No, because if I stop my pen right here, I'm touching 2 points at the same time. Okay? And the reason I talk about that is because what we're going to talk about today is a one-to-one function. A one-to-one function, that'll be the next thing I'm going to put up here. The one function, because my x's were different here, but my y's were not. And so all of these have to be different in order to be one-to-one. When I put them over here, now my x's repeat, and that is why it did not pass the vertical line here. Just to kind of show you what we're talking about with the vertical and horizontal line test. We already said that this one passed the vertical line test, right? If I hadn't graphed this new one here and I ask you, is this a one-to-one function? That means if I take my pen and run it up and down here, I'm touching more than 1 point right here, right? So that is not a one-to-one function. It passes the vertical line test, but it does not pass the horizontal line test. So I wouldn't even need to graph this new one if I wanted to determine if it's a one-to-one function, okay? If it passes both the vertical and the horizontal line test, then it's a one-to-one function. That would be one way, and you're going to have that question sometimes. On today's assignment, you might see that a little bit, but especially I know like on quizzes and tests, that's a question that we see. All right, last thing I'm going to talk about today. Very short lesson today. Proving inverses. Okay, so I'm going to write out a statement here, and it's going to kind of seem, might be a little confused by the statement, but I'll explain what it means. If A equals B, when f of A equals f of B, then the function is one-to-one. this would just be another way that we could do it. Like, let's say it's a function that I can't graph, or I don't know what the graph looks like. Then what I need to be able to do is prove that it is a one-to-one function, okay? The best and easiest way, it's kind of like solving a quadratic. The best and easiest way is let's use our calculator, right? But what if that's not available? What if we don't know what the graph looks like? This would be a way that we could algebraically determine if the function really is one-to-one. Okay, now I'm going to give you a really easy one that we already know is a one-to-one function, just to kind of show you how this would work. F of x equals 1/2 x minus 4. Okay, so now we already know what kind of function do we have here? It's linear, right? Y equals mx plus b, slope-intercept form, okay? And I know that if I graph slope-intercept form, it's a line, okay? All lines are one-to-one functions because does it pass the horizontal and vertical line test? Passes both of them, right? There's never a point where I will touch more than one point going either direction, vertically or horizontally. So I already know, okay? So one way to say it would be like, I already know that this is a one-to-one function because it's a line, and a line passes both the vertical and the horizontal line test. So that would be one way that you could prove or say. But here what we're going to do is we're going to prove it algebraically. So I want to get an answer of a equals b. So I'm going to plug a and b into the function. Kind of like we've done all year long. If I said let's evaluate f of 2, we're going to take 2 and we're going to plug it into the function, right? The only difference here is we're plugging in a letter, a variable. So we're going to plug a into the function. We're going to plug b into the function, okay? This is the function that we're dealing with. So first of all, I'm going to say f of a equals f of b. That's where I'm starting. I'm going to plug a and b into the function that I'm given. So I'm going to start off, and I'm going to go a into this function. So I'm going to go 1/2 times a minus 4. Over here, I'm going to go 1/2 b minus 4. We're just taking a, plugging it in, b, plugging it in. Pretty straightforward. But we want to know, will we end up with a equals b? So now we're going to kind of simplify the two sides. Well, what I could do first is add 4 to both sides. Those knock each other out. So now I have 1/2 a equals 1/2 b. How would I get rid of the 1/2? Multiply by 2. So I'm going to multiply by 2 on both sides, which makes 1. And we've proven that a equals b. So that's how algebraically we could prove. Now, do we have to go all through that? No, because we already said graphically we could do that. It'll be a lot easier to do it graphically. But if I had a more difficult equation to do, like maybe a cubic polynomial or maybe a quadratic polynomial where I wasn't sure if it is or not, and I don't know what the graph looks like for that graph, then I could do this one algebraically. Okay, I think that's all we got. All right, assignment for today. I've had a couple people have asked me, and I probably need to scan in my new keys. For a lot of these, because we got the new textbook, a lot of the page numbers have changed, but the assignments, for the most part, are still essentially the same. And so I've changed the the page numbers, but the assignment numbers have changed a little bit. So if you're looking at like my solution page, the page numbers aren't always going to match up because if I haven't scanned in the new one yet, then the problems and the correct page number are always listed right there in the post on Classroom. So if you ever need to go back to the right page numbers or whatever. But if you know it's 5-1, then you should know what page numbers it's going to be. And these are the numbers that we're going to do today. Okay? A function is one-to-one. I usually kind of make it a little bit, I kind of say one-to-one. I think it's a little bit easier to write it like that. If all x and y values are different. Okay. And so immediately on the last one that we did, we could tell that it's not going to be a one test. So in order to be one-to-one, and I'm going to show you an example of one-to-one here in just a second and show you what a one-to-one function would look like. There's lots of different examples that we could use, but I'll use a real basic one to kind of show you what a one-to-one function would look like. Okay, another key piece of information. If the inverse of a function is also a function, then we're going to name it F inverse. The terminology or symbol that we use for that is F to the negative 1 power. So that negative 1 that looks like an exponent is really read F inverse. And we're going to see that a lot when we start talking about inverses. And so just, you're not actually typing to the negative 1 power into your calculator, you're just reading that as the inverse of F. The negative 1 is not considered an exponent here, it's just what we use for terminology purposes. Okay, I'm going to give you a graph here. This graph over. I'm going to do the same thing I did just a second ago. We're going to graph a function and its inverse. And I'm going to show you a really quick and easy way to determine if a function is an inverse or not. And I'll go back to the graph we did just a second ago to kind of show you how that one was not, and we could tell that immediately without even graphing the other one. Okay, so if I gave you this equation, y equals 1/3 x plus 2. You could generate some points. I know typically when we graph this one, we don't necessarily generate points. We just say, I'm going to go up 2, make a point, and then I'm going to go up 1 over 3. I could also go down 1 and left 3, and it's going to continue just like that. And that would be my line. Once again, that would be something you could put into your calculator really quickly to graph it if you wanted to, but we've talked about a lot of different ways to graph the slope-intercept form. Pretty basic function, right? Now, if I were to draw this reflection line right through the middle here, When I flip this one over, you could solve it. I could say x equals 1/3 y plus 2. I could solve this for y and then put that into my calculator. So I could subtract 2 from both sides. And then to get y by itself, we could multiply by 3. So this would be 3 times x minus 2 equals y to get rid of the 1/3, which really becomes 3x minus 6. And then my slope is 3. So we're going to go up 3 over 1. We're going to go up 3 over 1. Up 3 over 1. And we see this point right here that sits right on that reflection line. My graph's not perfect, but it's pretty close. And I'm going to connect those together. So what I can kind of start to see, and that's why I put this reflection line in here. I can see that this point is reflected over here. This point was right on the line, so it stays where it's at. These points are going to reflect over here. You could take any point you wanted to off of that line, and you could determine that it is the inverse of that function. So the way that we would write this, first of all, is it a function? Well, the red line, is it a function? Absolutely, right? It's just a line. We know all lines are functions. The inverse is also a line, so if I did the vertical line test here, it would also be a function, okay? But if we wanted to just look at the original and determine if the original and the inverse are both functions, we could also do what we call the horizontal line test. And I could run a horizontal line up and down that, and I should only touch one point at any given time. If it passes both the vertical and the horizontal line test, then we would say that it's a one-to-one function. The other thing that I would say here too, based on what we talked about just a second ago, if I wanted to write my inverse here, I would write it like this. F inverse of x equals 3x minus 6. And I can write it like that because it is a function. If it's not a function, then we would just write it as an equation and leave it alone. But whenever it's a function, we can write it as a function, f inverse of x. If I go back